Okay, I think this will be the last of the supplemental videos. It's going to be slightly involved. Now, so far you probably would have seen the videos or heard about it elsewhere, read the book about the quadratic formula, right? Um, that's been a standard way of solving quadratic equations for a very long time. But as recent as a couple years ago, there was a paper that was published with an alternate method of solving quadratic equation, and it's very neat because it makes use of symmetry. Symmetry, a very powerful tool in mathematics. Now recall that parabolas have parabolas have this symmetry. All right. The most simplest one, x squared, if you look about the y-axis, it has symmetry. Now even if I were to move this parabola around to somewhere else, there is still a line I can draw about which it is symmetric. Or if I were to push this parabola down, I can still find this line about which it is symmetric. And then recall from the light property that I told you about parabola, this line that is the symmetric is the line that goes through the focus. Okay. Now let's look at some of the values that some of the quadratics that we have factored so far, right? So x squared plus 5x plus 6 equals 0. It gave me x equals -2 and x equals -3 right here. What was the next one? Yeah, x squared plus 6x plus 8 equals 0 gave me x equals -2 and x equals -4. How? Because that was the factored, so if this is 0, x is -2 and -4. Where's the other one? Oh, it's on the back side. X squared plus 6x plus 7 gave me this complicated one. So if this is 0, then x plus 3 minus root 2 is 0. So x is -3 plus root 2. X plus 3 plus root 2 is 0. So x is -3 minus root 2. Similarly, if this is 0, then x is -3.5 plus root 3.25, -3.5 minus root 3.25. Okay, let's fill that in there. X squared plus 6x plus 7 and x squared plus 5x plus 3. This gives me -3 plus root 2, -3 minus root 2, -3.5 plus root 3.25. Don't worry about the complicated values. Now in these two examples, can you notice the symmetry? Over here it's immediately obvious. What are these values of x? It's -3, and then you're adding something or you're subtracting something. So on the number line, what does that look like? If that point is -3, that's -3 plus root 2, and that's -3 minus root 2. What that means is these points are equidistant or equal distance from -3. That's pretty neat because it means that my answers for x are symmetric about this point, -3. Same thing goes for this one here, -3.5, and my answers for x are equal distant, right? Because I'm adding and then subtracting the same value. Okay, equal distance. So while it's more obvious here, it's not very obvious here, but we can still find a point here. So right here, if I take negative 2.5, then this point is negative 2.5 plus 0.5, which is negative 2. And the other value is negative 2.5 minus 0.5, which is negative 3. So it still follows the equal distance rule. And over here, if I take my midpoint to be negative 3, I have negative 3 plus 1, negative 2, and negative 3 minus 1, negative 4. So that's pretty awesome. Again, they are equal distance. So what's happening here? If you look at it graphically, what this is saying is if I were to plot this graph, then it hits the x-axis at negative 3, negative 2. And it's symmetric about this point, which is negative 2.5. Similarly, this guy here, it's negative 2, negative 4. And the midpoint is negative 3. Now that's not a coincidence. And these values that you see here, the negative 2.5, 3, 3, 3.5. Oh, this should be 2.5. These values are exactly the half of these. And they come from the fact that you can create the square. To create the square here, you take 2.5. Here you take 3. Here you take 3, and here you take 2.5. So, what's the method? So the method is based on this observation. Is that, let's say I'm trying to find x when this parabola equals 0 or takes the value 0, and I give you what the parabola looks like. So here's the method. I know that these two are the answers, right? I'm trying to find them. But from our current observation, I know that if I can find this value, right? If I can find this value, let's call this the axis of symmetry. If I can find this value, then this is just going to be this value plus a number, and this is going to be this value minus this number. All right. So let's give this parabola, let's say values, right? Let's say it's x squared minus 4x plus 4. Yeah, that'll work. All right. Now this value we know has something to do with this number. It's in the positive one, so this value is 2. So this is going to be, say, 2 plus alpha. And this is going to be 2 minus alpha because they are symmetric. Now we go back to the splitting the middle term, right? The direct method. What was the idea there? You're trying to find two numbers whose sum is 6 and whose product is 8. So we are saying that those numbers are 2 minus alpha and 2 plus alpha. What's the sum? The sum is 4. Right, which makes sense. And the product has to be 4. What's the product? 2 minus alpha, 2 plus alpha equals 4. But wait a second, what is this? This is the difference of squared, but applied in the reverse. You have a minus b and a plus b. So this becomes 4 minus alpha squared equals 4. Oh, let's make this 3. Otherwise, it's not going to work. So 4 minus alpha squared is 3. So you get 1 is alpha squared, or alpha is 1. So what are the values? The values are 1 and 3. You can verify that. When x is 1, this becomes 1 plus 3, 4, minus 4, 0. When x is 3, 9 plus 12, minus 12, 0. This is a rather new way of solving quadratic. It was only discovered a couple of years ago. Discovered and formalized a couple of years ago. But the point of these videos are to show you the different ways in which you can think about quadratic equations, why we look at solving them, the relation between the graphs, the symmetry, the area thing, taking a different route to converting sums into products, and just general notion about why parabolic shapes are important. It turns out that all motion that is governed by gravity is parabolic in nature, so it's very important to understand its property. And one last thing, there's also a very neat way in which parabolas are created in nature. These are just some experiments. Let's say I fix a point right here, a point O, and I ask what are all points equal distance from O. Say 5 centimeters. What is the set of all points that are equal distance from O? If you think about it, you can pause the video and think about what would that shape look like. You would be able to conclude that it would look like a circle, right? That's the definition of a circle. The radius is the same, right? So if I take one point and I find all points which are equal distance from that point, that shape comes out to be a circle. Now let's say I ask the next question. I was like, well, what if there are 2 points? If I take AB, same question. What are all points equal distance from A and from B? Now the first one is obvious. You connect A, B, and you take the midpoint. What about the next? Can I have a point here? No, because it's going to be closer to A than B. Can I have a point here? No, it's going to be closer to B than to A. So all I can have are all these points which go up and down. So here, this is what is called a bisector. It bisects this line AB. So we get a circle there. If I take 2 points, I get this straight line. And then, of course, the next question is, well, what if I make it, let's say, now I want something more complicated. I take a point, and then I also take a line. Let's say I call this L1. So now, what are all points equal distance from O and the line L1? Now the first candidate is obvious. Again, we draw this perpendicular and we look at the midpoint. But now let's see. I can't have anything to the left of this line because that's going to be closer to the line than to the point, right? And I can't have anything here because that's going to be closer to the point than to the line. Now if I go straight up here like I did in this previous case, again that's not going to work because then I'm further from the point than from the line. So I'm going to have to turn in such a way that for any point this distance equals this distance. It doesn't look like in this figure, but that's because my drawing is not accurate. But this shape turns out to be a parabola. So it has this neat property that there exists a point which coincidentally is the focus. Every point on the parabola is equal distance from a point and some line. And they have special names and all, which is not important, but that's another way in which you can generate a parabola. The last one, this video is getting a little lengthy, is you can generate these shapes from a cone. If I take a cone, now say I slice this cone right over here, what do I get? If you take a few seconds to imagine, this shape would be a circle. If I take any parallel slice of a cone, it's going to be a circle right there. I take the cone, now I use an oblique line. It's still going to be round, but it's not going to be a circle. It's going to be an ellipse, which we will study later towards the last couple of weeks in this course. Now let's say I turn this line further, I spin it further that way, I make a cut that way. Then I would get a shape which should remind you of a parabola. In fact, it is a parabola, because you have this opening here, so the shape you get when you slice the cone this way is a parabola. That's another way in which parabolas can be generated. So it's a very rich theory. It occurs in a lot of ways, there's a lot of properties, but in this class we are going to focus on the algebra part of it. But I just wanted to give you a hint, a taste of like just the interconnectedness between the geometry, the algebra, interpretation as areas, etc.